The last speaker of the day is Demetres Armanes, who's the managing principal and research engineer for ABS. Demetres is currently, he also holds a PhD in intelligent control and also in electrical and electronics engineering in the University of Liverpool. Interesting to find out how you managed to understand the Liverpoolians, but maybe we can have a chat about that later on. Thank you very much. Thanks, Demetres. Please.
Hello, everyone. Thank you for sticking around. And I think I would like just to try to keep you engaged in this last session of this wonderful event. I would like to just try to take your mind from information management that we have been discussing all this time to another great challenge of our days. This is energy management. So to address the topic of automation in general, I would like to think of it as removing responsibilities from the human in the loop and changing its scope of work and how we can do that efficiently and we can provide trust to the technology. So, in short, human boards have two main responsibilities: to manage information and to manage energy. What is energy? I just like to address these basic dimensions of energy for those of you that are not engineers. Energy is power times time. Traditionally, we have been, in the marine designing and shipbuilding, we have been concerned about enough installed power on board to account for any unforeseeable event or safety situation that, in reality, happens very rarely. In reality, what happens? Power fluctuates all the time. It changes. Propulsion power changes due to ever-changing waves, currents, winds, and other parameters on board. Electrical power changes because consumers come online and going offline. How much and how fast power fluctuates with time is one important and fundamental element to understand the energy footprint of any asset, system, or any other situation. The other part of energy that is very important is cannot be created nor destroyed. It can only change from one form to another, and how efficiently this conversion of energy happens is one other fundamental concern about energy management. So I hear, and I have been in this field of matching information technology and operational technology for some time now. People are talking about big data, talking about connectivity on board, but the fact is, reality, it's very difficult to be digitalized. There are so many different physical phenomena that you need to take into account that you cannot hope to transfer everything on shore and take decisions there. So decisions are made on board in a split second, every day of every year of the vessel, and these decision makers are not the humans. It's the automation that we have implemented on board, and gradually through the years, we have removed our crew from the decision making up to the level of decision making to a more managing position of this kind of situation. To illustrate that in a more vivid way, I have created this energy flow mapping just for your consideration on a cruise ship. So what you see here, I have mapped the energy flows of 6 primary players, which is the fuel, the low temperature water, the exhaust gas, the high temperature water, the electrical energy flow, and the steam. What you see here is the width of each arrow is demonstrating kilowatt hours for each of these energy flows. As you understand, this is frozen in time. If I was able to animate this diagram here, you will be observing the width of the arrows changing along the timeline, and their relationship changes as well because of the efficiency points operating all these different machineries. So this is exactly what we're trying to achieve on board, how to manage that in real time more efficiently. Because if you don't start from that, to go up to the total problem, it's a bit unmanageable, as the colleagues here have been presented before, because it's a multi-decision objective optimization. You have to have many parameters to optimize, and you need to start from the building blocks of the problem to optimize what you can. So, to illustrate my point in a very specific system that can be used as a great example of how model-based system engineering is here to help us address this energy management problem and the information management problem as well, I have used a typical pumping system because it's everywhere on board, and we can relate to that pumping system even if you are not technical people. So a pumping system accounts for nearly 20% of the world's energy used by electric motors. 20% of the world's energy. It accounts around 25 to 50% of the electrical energy consumed on board. So, such system should be optimized. It's very important, right? But where to start? Where to start thinking how to optimize it? I have grouped here the total life cycle cost of a pumping system, a typical pumping system. 4 main categories: the initial costs, the maintenance costs, the energy costs, and under the other cost category, I have grouped smaller categories like installation, operational costs, downtime, environmental, commission and disposal costs, etc. So evidently from this graph, we need to focus in 2 main categories: energy costs and maintenance costs. And we argue in my group that you can do that, our clients can do that, with a small investment in the initial cost of the system. And let me clarify what I mean with that. Model-based system engineering was not a norm in shipbuilding. We have designing our systems based on the traditional orange line of system engineering, iterative cycles until we reach to an optimal design point, and then all this data and decision-making, trade-offs, gone. The system has been delivered, and the acquisition cost starts for the owner and operator at the very end of this graph. Imagine that this is only the 15% of the total cost of the system. So if I was to extend these 2 lines in time, you will observe them to expand until they drop to 0 after the decommissioning and disposal costs. Also, their difference expands as well. So what we're trying to do in my team is to help our clients migrate from riding the orange line of the systems engineering lifecycle cost to ride the blue line of the model-based system engineering. Because we have already created an enormous investment in the factors that relates to model-based system engineering benefits, and we're ready to deliver to our clients the model-based system engineering factors that provide these gains. And that is nothing else but risk reduction of the system, improved communication between all the parties, the vendors, the shipyards, the operator, improved energy costs, improved maintenance costs, and of course, standard conformance and traceability through our normal engineering review plan. Let's see now how model-based system engineering, for this particular case study I'm exploring today, can help us reduce energy costs. Some of you may know, for any pumping system that requires flow control, we make use either bypass lines or throttling valves or even pump speed control. From these 3, pump speed control is the most efficient one because with less speed imposed on the pump, less energy is imparted to the fluid and less energy needs to be bypassed or throttled away. From the various options to control the speed of the pump, there are one very popular one that is called variable frequency drives, or VFDs. Not all systems, though, are suitable for variable speed pumping control, and through model-based system engineering, we can explore which systems under which operating condition of a real vessel will have the biggest benefit of applying something like that. In this particular example, that particular vessel was suitable for this kind of upgrade, and now we are able, through that process, to explore the various control options. I recall, automation is all about decision-making. It's all about who is taking the decision when. So automation is not static. Control algorithms is an active research field, especially now more than ever, where sensors integrate various aspects on board, and we have more decision points to take into account. So if you go back and check your vessels that have been designed 10 years ago, you will observe that automation is very, very primitive. Can be upgraded, can provide benefit, and through that kind of studies, you can get results just by changing the code on board, nothing else. So in this example, we are exploring 3 control options for this particular vessel of the pumping system, of the central cooling system, for instance. The first one is to let it run as it is. You know, the pump runs at full speed, at design speed, all the time for the whole year, and we calculate the total fuel consumption of that pump running at that speed constantly. On the low graph, we see the cooling efficiency of that control algorithm. So how about if we change that? How about if we have an option to decide above the temperature threshold for the needs of the main engine cooling, the pump to run at its maximum speed, and below that level of cooling requirement, the pump to run at a minimum speed. How that will affect my total fuel consumption of the gensets? And the result is the blue line, the blue graph on the top side, and also the cooling efficiency of that control strategy on the lower side. Let's play around a bit on that concept and change the threshold. So we have a third control strategy now with better performance at total fuel consumption for the full year, but less so on the cooling efficiencies. All of them, however, well beyond the engine maker recommendation under the safety limit. So all of them are applicable and can be upgraded on board. So we have established that by reviewing the control strategies, we can find points that by changing the software on board, the control software, we can optimize the energy management, the real-time energy management, what matters most. Now, the next step is to ask our vendor, our solution provider, to give us the solution. But this is even more challenging. How well the developer on that particular vendor will be able to define our requirements in their controller. How well they take into account all the real signals, all the electromagnetic compatibility issues, all the IOs that will effectively, this controller will have to account for on board. And this is where the model-based system engineering approach can help us, again, establish the performance of the controller even before any contract has been signed. So the vendor can now have a way to test and prove to you that what they are going to deliver, the actual hardware on board, will be performing according to the requirements we have identified. And this is very important because from there on, the design can change. You have a controller, you know that what we are going to include on board will change the harmonics distortions, for instance, on board your vessel. You calculate the filtering, and so you have a lot of work to do even before you have considered creating a contract or asking a vendor to implement something like that. After that, when we have completed this test, because we are helping a lot with this kind of review and approval process, we take advantage of the digital twin, if you like. I don't like that terminology at all because it's very generic. I would say the model, the physical model of the system, and going a step forward. And here where information technology comes into play. So there are various condition monitoring techniques out there. Most of them we have recognized under our publications. One particular condition monitoring technique I like is performance trending. performance trending uses any kind of data sets or signals from the system on board to create trends. One huge disadvantage of this technique, however, is the baseline data. So when we start reviewing this information that comes on board, we don't have something to compare against. So if you don't have something to compare, you cannot identify the gaps. You need to have more time to create these trends. Having the model created in the previous step, where you identified the optimization of the control loop, gives you that baseline of signals that you cannot digitize. You cannot pass through the limited bandwidth of your satellites, and you don't have them on shore. You need to be able to create frequencies in several megahertz where they cannot be digitized. So that kind of approach bridges the gap between operational technology and information technology, and when your bandwidths are low and you cannot get that insight you need for decision making, model-based system engineering can fill these gaps. And you can start creating trends, and you can start performance maintenance over the condition of the equipment, and enables a new approach that we call energy-centered maintenance, where it matches the traditional preventive and predictive maintenance tasks with insights of the efficiency of the equipment to trigger maintenance actions based on the efficiency of the system. So, concluding, I would like to take this concept of model-based system engineering and automation performance validation and take it to a modern shipbuilding project. What you see here is the work we are doing with a shipyard and a major vendor for an LNG carrier that meets the requirements for 2050. Central to this design is the smart energy management component. So the responsibility of how this vessel is operating is on the code that is going to take decisions to integrate all various energy sources in real time, find the optimum way of operating between various processes in real time, and delivers that results. There is no way to design that vessel without model-based system engineering, without a test bed of all these control strategies running in extreme conditions that you cannot test in factory acceptance testing, in integration testing, or in sea trials, because the time is not there. The conditions may be prohibited due to safety reasons or other economic factors. So the only way forward for the digital ship of the future is through model-based system engineering. Thank you very much, and good to have you.